So what kind of forces do we know that aren't conservative, that we can't find a potential for? Well, time-dependent, velocity-dependent. How come kinetic friction? That's not, is that time-dependent? Like in this problem, except that where it's sliding, yeah, that part. Where it's sliding, where's the time dependence? Is there any? Force is constant, right? How come it's not conservative? Yeah. Is it an example of a velocity-dependent force? Yeah.
If velocity is zero, then friction isn't doing any more. So yes, it is velocity.
Well, it's true that, but if for any force, if you don't displace, then there's no work involved, right? But there is something important that happens if you were to try to, yeah. Yeah, the subtle dependence on velocity, she nailed it. It depends, it's opposite always, and so it is subtly velocity dependent. It reverses when velocity reverses. And so, yeah, you're right, that ends up manifesting itself as energy showing up as heat. Okay, does this look chemically familiar? Is this what you guys are doing this? No, so you've forgotten it by now? Is that okay, fine. Yeah. All right. So that might be the intermolecular potential. So as a function of the bond length, that's the potential energy. And the minimum would be, let's say, at R0, and the depth we might characterize. Basically, only those two numbers are needed to try to get a rough idea of what's going on. What's the binding energy in this one? U0? Yeah, so the binding energy is the energy I have to take to go to infinite remove, to get out of the well, for R to go to infinity. Suppose that this little unhappy molecule, however, doesn't have enough. It only has as much energy as shown there in the red line. So it's more than the minimum, but not much. What will it do? Cry, yes, and oscillate between the turning points, right? Between that, has Parkinson's too. Between that point and that point. And it will just go back and forth. Yeah, actually, it will go back and forth. Yeah, all right, fine.